Hello 10th class students. As many of you will be opting for MPC group or a BIPC group in near future, and many of you will be writing the different competitive exams. So here I am going to extend the topic of periodic classification of elements to the next level. So these videos are related to that part. Okay, they are again related to concepts only. Based on the concepts, just a little bit of extension of the topics which you have to go through once. Okay, so go through these videos very carefully. Try to understand the maximum concepts which are available in this particular videos. Thank you.
In this video, we're going to look at the periodic table and we're going to classify the elements into groups. And so as we go through these terms, I'm going to be checking them off. So the groups are the vertical columns on the periodic table. And so if I go over here, I can see that all of these elements are in the same vertical column. So all of these elements are in the same group, and we call this group 1. I can see that all of these elements are also in the same column, right? So all these elements are in the same group, and we call this group 2. I can continue labeling my groups. This would be group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then I go back up to here and I can see I have another vertical column, so group 13, 14, 15, 16, 17, and finally 18. So that's one way to number your groups. There is another way to number your groups, and that would be to say that group 1 is group 1A, group 2 is group 2A. And then, kind of ignoring groups 3 through 12, continue on with your numbering system. So 1A, 2A, that would make this group 3A, group 4A, group 5A, group 6A, 7A, and finally 8A. And this second way of numbering your groups is useful when you're thinking about valence electrons. And so let's move on to the concept of periods, right? So a period is a horizontal row on the periodic table. And so if I look at period 1, and I just move across my periodic table, right? Hydrogen is in the first period, and so is helium. I move on to the second period, so lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And so I can continue with numbering my periods. So this would be period 3, 4, 5, and 6. Now notice I don't have the entire periodic table on this video. I didn't have enough room, and we're not really going to talk about all of those elements anyway. So let's go ahead and focus on metals next. And so let's talk about the alkali metals. And so when I'm talking about metals, I'm going to try to write in red here. So the alkali metals are found in group 1 or group 1A. So things like lithium and sodium, potassium, right? So here are my alkali metals. The alkali metals are soft silvery metals that are extremely reactive. And one nice thing about organizing the elements into groups is elements in the same group have similar chemical properties, and so the alkali metals react in similar ways. For example, all the alkali metals will react with water. And the alkali metals turn out to be so reactive that you're not going to find them in their pure state in nature. You're not going to walk outside and find some sodium lying on the ground. Okay, they're found in nature in combination with other elements. All right, let's talk about hydrogen, because hydrogen is also in group 1, but hydrogen is not an alkali metal. Hydrogen is a non-metal. So let me go ahead and draw that in green here. So I will represent non-metals in green. So hydrogen is the exception in group 1. Next, let's talk about the alkaline earth metals. So you find those in group 2 or group 2A, so right in here. So things like magnesium and calcium and strontium are your alkaline earth metals. Your alkaline earth metals are reactive, not quite as reactive as the metals in group 1, but you don't find these in the pure state either. You find them in combination with other elements. And so once again, the alkaline earth metals are going to react in similar ways. They have similar chemical properties, and so that's, again, a convenient way of organizing the periodic table into groups. So for right now, let's just go ahead and say groups 3 through 12, right? These are all metals in here. And let's just talk about metals in general for a minute. So metals the properties of metals. So metals are solids at room temperature, except for mercury. So here's mercury down here, which is a liquid at room temperature. Metals are very malleable, which means that you can form them into different shapes. They're very workable. They're not brittle. Metals are also ductile, which means you can draw them into wires. You can form them into wires. For example, like copper. So here's copper right here. So copper wires, of course, carry current in homes, right? So metals are good conductors of heat and electricity, and so those are the properties of metals that most textbooks will talk about. So let's contrast those with nonmetals. Right, so nonmetals, if you have a solid nonmetal, those solids would tend to be brittle, not malleable like metals. Nonmetals are poor conductors of heat and electricity. So you find nonmetals in different states of matter. So let's talk about one of the nonmetals now, and that would be the halogens. And so let's find the halogens on our periodic table. You find them in group 7A or group 17, and so things like fluorine, chlorine, bromine. So here are your halogens right in here. So halogens are very reactive nonmetals. So they're often very colorful, very corrosive. And the name halogen actually means salt former, and so we're actually going to come back to that in the next video when we look at some electron configurations and we talk about why these things are so reactive. And so those are the halogens. Next, let's find the noble gases. So the noble gases are found in group 8A or group 18. So some of these are very famous, like helium, neon, argon, krypton. All right, so here are your noble gases. They're colorless gases, and they're generally very unreactive. And so once again, we'll talk about why in the next video when we talk about some electron configurations. All right, so there are some other nonmetals on here, which I will identify in a minute. First, I want to talk about the fact that you pretty much find metals on the left side of the periodic table, right? So let me go back to the red color, and you can see, right, I have all these metals over here on the left side. And then for my nonmetals, right, in green, you're going to find those over here on the right side of your periodic table. And so the dividing line between those, let me go ahead and draw it in there. It's kind of a zigzag line. So let me see if I can sketch it in here. So the dividing line would go something like this. All right, so we're going to go a zigzag line down our periodic table. And some of the elements that you find on this zigzag line have properties in between those of metals and nonmetals, and we call those metalloids. So let's go ahead and talk about metalloids now. So metalloids, right, oid of course being like a metal, so it's similar to metals, but again the properties are in between those of a metal and a nonmetal. So some of the elements that are considered to be metalloids would be boron right in here, so silicon, germanium, arsenic, antimony, tellurium, and sometimes you'll see acetine listed as one. So it depends on which textbook that you're looking in. So you can see that some of the elements along this zigzag line are considered to be metalloids, and there's no official one definition for which elements are considered to be metalloids, and so you might see a little bit of a discrepancy there for some of these elements. But in general, those are the ones that are considered to be metalloids, and silicon probably being the most famous one, right? So silicon is a semiconductor, right? So it's a metalloid, so it's like a metal, so it does conduct electricity, but not to the same extent that a metal would. And so these intermediate properties are sometimes useful. And so let's go ahead and mark some of the rest of these, right? So these would be some other metals, right? And then over here on the right would be the rest of your nonmetals here. So carbon is a nonmetal, nitrogen is nonmetal, oxygen is nonmetal, phosphorus, sulfur, and so that's just a quick way to divide the periodic table up with some simple definitions. All right, so in the next video we'll talk more about the electronic structure and we'll get into definition of transition metals.
So let's talk a little bit about groups of the periodic table. Now, a very simple way to think about groups is that they just are the columns of the periodic table. And a standard convention is to number them. This is the first column, so that's group 1. Second column, third group, fourth, fifth, sixth, seventh, eighth, group 9, group 10, 11, 12, 13, 14, 15, 16, 17, and 18. And I know some of y'all might be thinking, what about these F block elements over here? If we were to properly do the periodic table, we would shift all of these, everything from the D block and P block all rightwards and make room for these F block elements. But the convention is that we don't number them. But what's interesting, why do we go through the trouble about calling one of these columns, a group? Well, this is what's interesting about the periodic table, is that all of the elements in a column, for the most part, and there's tons of exceptions, but for the most part, the elements in the column have very, very, very similar properties. And that's because the elements in a column or the elements in a group tend to have the same number of electrons in their outermost shell. They tend to have the same number of valence electrons. And valence electrons and electrons in the outermost shell, they tend to coincide, although there's a slightly different variation. The valence electrons, these are the electrons that are going to react, which tend to be the outermost shell electrons. But there are exceptions to that, and actually there's a lot of interesting exceptions that happen in the transition metals in the D block. But we're not going to go into those details. Let's just think a little bit about some of the groups that you will hear about and why they react in very similar ways. So if we go at group 1, and hydrogen is a little bit of a strange character because hydrogen isn't trying to get to 8 valence electrons. Hydrogen in that first shell just wants to get to 2 valence electrons like helium has. And so hydrogen is kind of it doesn't share as much in common with everything else in group 1 as you might expect for, say, all of the things in group 2. Group 1, if you put hydrogen aside, these are referred to as the alkali metals. And hydrogen is not considered an alkali metal. So these right over here are the alkali metals. Now, why do all of these have very similar reactions? Why do they have very similar properties? Well, to think about that, you just have to think about their electron configurations. So, for example, the electron configuration for lithium is going to be the same as the electron configuration of helium. And then you're going to go to your second shell, 2s1. It has 1 valence electron. It has 1 electron in its outermost shell. What about sodium? Well, sodium is going to have the same electron configuration as neon. And then it's going to go 3s1. So once again, it has 1 valence electron, 1 electron in its outermost shell. So all of these elements in orange right over here, they have 1 valence electron, and they're trying to get to the octet rule, this kind of stable nirvana for atoms. And so you can imagine is that they're very reactive, and when they react, they tend to lose this electron in their outermost shell, and that is the case. These alkali metals are very, very reactive, and actually they have very similar properties. They're shiny and soft, and actually because they're so reactive, it's hard to find them where they haven't reacted with other things. Well, let's keep looking at the other groups. Well, if we move one over to the right, this group 2 right over here, these are called the alkaline earth metals. Alkaline earth metals. And once again, they have very similar properties, and that's because they have 2 valence electrons, 2 electrons in their outermost shell. And also for them, not quite as reactive as the alkali metals, but let me write this, alkaline earth metals. But for them, it's easier to lose 2 electrons than to try to gain 6 to get to 8. And so these tend to also be reasonably reactive, and they react by losing those 2 outer electrons. Now, something interesting happens as you go to the D block. And we studied this when we looked at electron configurations. But if you look at the electron configuration for, say, scandium right over here, let me do it in magenta. The electron configuration for scandium, so scandium's electron configuration is going to be the same as argon. It's going to be argon. the Aufbau principle would tell us that the electron configuration, we would have the 4s2 just like calcium, but by the Aufbau principle, we would also have one electron in 3d. So it would be argon, then 3d1, 4s2. And to get things in the right order for our shells, let me put the 3d1 before the 4s2. And so when people think about the Aufbau principle, they imagine all of these d block elements as somehow filling the d block. Now, as we know in other videos, that's not exactly true, but when you're conceptualizing the electron configuration, it might be useful. Then you come over here and you start filling the p block. So, for example, if you look at the electron configuration for, let's say, carbon, carbon is going to have the same electron configuration as helium, and then you're going to fill your s block, 2s2, and then 2p12, so 2p2. So how many valence electrons does it have? Well, in its second shell, its outermost shell, it has 2 plus 2. It has 4 valence electrons. And that's going to be true for the things in this group. And because of that, carbon has similar bonding behavior to silicon, to the other things in its group. And we could keep going on for example, oxygen and sulfur. These would both want to take 2 electrons from someone else because they have 6 valence electrons. They want to get to 8, so they have similar bonding behavior. You go to this yellow group right over here. These are the halogens. So there's a special name for them. These are the halogens. And these are highly reactive because they have 7 valence electrons. They would love nothing more than to get 1 more valence electron. So they love to react. In fact, they especially love to react with the alkali metals over here. And then finally, you get to kind of your atomic nirvana in the noble gases here. And so the noble gases, that's the other name for the group 18 elements, noble gases. And they all have the very similar property of not being reactive. Why don't they react? They have filled their outermost shell. They don't find the need. They're noble. They're kind of above the fray. They don't find the need to have to react with anyone else.
Now that we've classified our elements into groups on the periodic table, let's see how to determine the number of valence electrons. And so for this video, we're only talking about the valence electrons for elements in the main groups. So when we talk about the main groups, you're using the 1 through 8 system for classifying groups. So 1, 2, 3, 4, 5, 6, 7, and 8. So we're going to ignore the other way to number the groups, and so therefore we're going to ignore groups 3 through 12 for this video. And so if you're talking about the main groups, the valence electrons are the electrons in the outermost shell, or the outermost energy level. And so let's see if we can figure out how many valence electrons sodium has. So for sodium, all right, if I wanted to write an electron configuration for sodium, I assume you already know how to do these. So you would say it is 1s2, 2s2, 2p6, and that takes you all the way over here to neon, and then that brings you to the third period, or the third energy level, and you have 1 more electron to worry about, and so that electron would go into a 3s orbital. So the full electron configuration is 1s2, 2s2, 2p6, and 3s1. When I want to figure out how many valence electrons sodium has, right, the number of valence electrons would be equal to the number of electrons in the outermost shell, the outermost energy level. For sodium, sodium has the first energy level, second energy level, and the third energy level. The outermost energy level would, of course, be the third energy level. So if I see how many electrons sodium has in its outermost energy level, right, it's only 1 this time. So that means that sodium has 1 valence electron. And that's very convenient because sodium is found in group 1. And so we can say that for main groups, if you want to figure out how many valence electrons you have, right, it's just equal to the group number, right? So the group number is equal to the number of valence electrons. And so that makes everything really easy. And so if I wanted to represent a neutral atom of sodium with its 1 valence electron, I could draw sodium here, and I could draw 1 valence electron next to sodium like that. All right, let's go ahead and write the electron configuration for chlorine next. So here's chlorine over here. And so if I wanted to write the electron configuration for chlorine, it would be 1s2, 2s2, 2p6, and once again that takes me all the way to neon. And so now I'm over here in the third energy level, or the third period. I can see that I would fill 3s2, so 3s2, and that puts me into my p orbitals. So how many electrons are in my p orbitals? 1, 2, 3, 4, 5. So I'm in the third energy level, I'm in p orbitals, and I have 5 electrons. And so that would be the electron configuration for chlorine. If I want to figure out how many valence electrons chlorine has, I have to look for the electrons in the outermost shell, or the outermost energy level. So I have, once again, the first energy level, the second energy level, and the third energy level. So I want the total number of electrons in the outermost energy level. So how many electrons are in the third energy level? Well, there's 2 and 5 for a total of 7. So chlorine has 7 valence electrons. And once again, that's very convenient because chlorine is in group 7. And so let's go ahead and draw chlorine with its 7 valence electrons. So here is chlorine, right? So 1, 2, 3, 4, 5, 6, and 7, like that. And so the reason I picked sodium and chlorine is, of course, because sodium and chlorine will react together to form sodium chloride. And let's analyze what happens using our electron configurations. And so sodium is going to lose 1 electron. So a neutral atom of sodium has equal numbers of protons and electrons. But if sodium loses its 1 valence electron, so it's going to lose its 1 valence electron, and I can show its 1 valence electron actually is moving over here to the chlorine. So now when I draw sodium, right, I have to represent it as an ion, a cation. Sodium used to have equal numbers of protons and electrons, but it just lost 1 electron. Therefore, it's left with an unbalanced number of protons, right? So it has 1 more proton than electrons, so it gets a +1 charge. So Na plus is the sodium cation. The sodium cation is stable, and the reason why has to do with the resulting electron configuration, right? So if I look at the resulting electron configuration, right, let me go ahead and use yellow here. It would be 1s2, 2s2, 2p6. And so the electron configuration for the sodium cation is the same as neon, which is a noble gas, and we know that noble gases are generally unreactive, and that has to do with the fact that their electron configurations are full in their outermost energy level, right? So the sodium cation is stable because it has an electron configuration like that of a noble gas. So for chlorine, right, if we think about how chlorine reacts, chlorine has 7 valence electrons, and let's find it on our periodic table here. So here is chlorine. Chlorine has 7 valence electrons. If chlorine gets 1 more, then chlorine would have an electron configuration like a noble gas, like that of argon. So chlorine will gain an electron here. So let's go ahead and write the new electron configuration if a neutral atom of chlorine picks up an electron, right? The electron would add right in here. And so instead of 3p5, right, we would write 3p6. And so the electron configuration for the chloride anion would be 1s2, 2s2, 2p6, 3s2, 3p6. So let me just go ahead and highlight that. 1s2, 2s2, 2p6, 3s2, and then 3p6. Let's go ahead and draw it, right? So we're no longer talking about a neutral chlorine atom here. We're talking about a chloride anion that picked up 1 electron, right? So it took that electron from sodium. So I'm going to show that electron in red has moved over here to chlorine like that. And so chlorine gains an electron. So it used to be overall neutral. It used to have an equal number of positive charges and negative charges, but it just added 1 more electron, right? So that gives chlorine a negative charge, so it's now the chloride anion. And so you have an ionic bond that forms between the sodium cation and the chloride anion here. So the attraction of these opposite charges forms an ionic bond. And so this is an example of a group 1 alkali metal reacting with a halogen, right? So in our video on the periodic table, we talked about elements, right? We talked about these being our alkali metals, and since these alkali metals are all in group 1, they all have 1 valence electron. And we talked about our halogens over here as also being extremely reactive, and the reason they are so reactive is if they add 1 more electron, they have the electron configuration of a noble gas. And so drawing the electron configurations thinking about valence electrons and thinking about the resulting electron configurations allows you to figure out how these things react. And so that is the reason why we can say that group 1 metals are so reactive, and why we can say that group 7, the halogens, or 17, are so reactive. It's because of this concept of electron configurations and drawing out your valence electrons. And so we could figure out how many valence electrons something else has, right? So let's say we were asked to figure out how many valence electrons oxygen has. Right, so all we would need to do is look at the group number, right? So this would be oxygen is in group 6, and so therefore oxygen has 6 valence electrons. And so if you wanted to represent oxygen with its 6 valence electrons, you could go ahead and draw in 6 valence electrons like that. And so that's a very useful thing to think about, that if you want to find the number of valence electrons, right, think about the group number for main group elements. In the last video, we saw the classification of elements into groups on the periodic table, and we stopped with the definition for a transition metal. There are 2 ways to think about transition metals. So one way to think about it would be when some teachers say transition metal, they're talking about elements found from groups 3 through group 12. So all of the elements in here, some people consider these to be the transition metals. So these are the elements found in the d block, right? So we're talking about d orbitals here. So you have to understand electron configurations for this video. So that's one way to think about the transition metals, but that way is maybe a little bit too general sometimes. So there is another definition, which you'll find on the IUPAC website. IUPAC is an acronym for International Union of Pure and Applied Chemistry, and they say that a transition element refers to an element whose atom has an incomplete d subshell. So when you're talking about the d orbitals, we already know there are 5 d orbitals, and each orbital holds a maximum of 2 electrons. So 5 times 2 is 10. So 10 would be the maximum number of electrons that you could fit in your d orbitals or your d subshell. So let's count that out on our periodic table. So 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for our d block. So let's go ahead and write an electron configuration for a transition metal, and let's see how that applies to our definition from IUPAC. So let's write an electron configuration for iron. So here's iron right here, and if I wanted to write an electron configuration, let's say I wanted to do noble gas notation. So once again, I'm assuming that you know how to do this already, so I won't spend too much time talking about it. But if I wanted to write a noble gas configuration, I would go to argon, which is the noble gas before iron, and I would put argon in brackets like that. And that takes me to the 4th energy level, or the 4th period on the periodic table. And then just looking at the periodic table, I can say, oh, that would be 4s1, 4s2, so I can write 4s2 here. And then I'm in my d orbital. So again, just looking at the periodic table to write my electron configuration, I would say 1, 2, 3, 4, 5, 6 electrons. So that would be 3d6. And I could have written this 3d6 4s2, and right now both are considered to be correct answers. And I won't get into a discussion about the order of filling of these orbitals in this video, so I'll save that for another video. This video is only talking about definitions and identifying elements on the periodic table. And so either one of these would be a correct electron configuration. And when I look at the d orbitals, right, so when I look at the d orbitals for the electron configuration, I can see that there are 6 electrons in my d orbitals. Well, that's an incomplete d subshell, right? Because I can fit a total of 10 into my d orbitals. And so iron would be an example of an element whose atom has an incomplete d subshell. So iron is a transition metal. Let's write the electron configuration for zinc. So let's find zinc over here. So right there on our periodic table. So if I wanted to write the electron configuration for zinc, once again, I would go to the noble gas before it, which is argon. So I would put in brackets argon right here. And then once again, it takes me to the 4th energy level. So 4s1, 4s2. So 4s2. And then I count over for my d electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it'd be 3d10. And once again, I could have written that argon in brackets 3d10 4s2, so it doesn't matter. So let's think about the definition for a transition metal, an element whose atom has an incomplete d subshell. Well, if I look at the d orbitals for zinc, right, they are completely full. I have 10 electrons in my d orbitals, and so this is a complete d subshell, so this does not meet the definition for a transition element. Now, also in the definition, it talks about cations, right? So let's think about the cation that zinc would form. Zinc would go to zinc 2+. So if I wanted to write the electron configuration for zinc 2+, I need to think about where does zinc lose 2 electrons. So if you're going from a neutral atom of zinc, right, to zinc 2+, you would have to lose 2 electrons. Well, I already know that those 2 electrons are going to be lost from the 4s orbital. So you're going to lose these 2 electrons right here on your electron configuration. And so you'd be left with 3d10. And once again, you have a cation that has a complete d subshell. You've completely filled your d orbitals. And so the cation does not have an incomplete d subshell, which means that it doesn't fit our technical definition for a transition element from IUPACs. And so once again, there are 2 ways of thinking about it. One's a very general way. So you might hear someone talk about an element from groups 3 to 12 as being a transition metal, or you might find people who are a little bit more particular about the definition who go along with IUPAC. So it's good to be aware of both ways of thinking about it.
Let's think a little bit about the notion of atomic size or atomic radius in this video. And at first thought, you might think, well, this might be a fairly straightforward thing. If I'm trying to calculate the radius of some type of circular object, I'm just thinking about, well, what's the distance between the center of that circular object and the edge of it? So the length of this line right over here, that would be the radius. And so a lot of people, when they conceptualize an atom, they imagine a positive nucleus with the protons in the center right over here, and then they imagine the electrons on these fixed orbits around that nucleus. So they might imagine some electrons in this orbit right over here, just kind of orbiting around, and then there might be a few more on this orbit out here, orbiting around out here. And you might say, okay, well, that's easy to figure out the atomic radius. I just figure out the distance between the nucleus and the outermost electron, and we could call that the radius. And that would work, except for the fact that this is not the right way to conceptualize how electrons, or how they move, or how they are distributed around a nucleus. Electrons are not in orbits the way that planets are in orbit around the sun, and we've talked about this in previous videos. They are in orbitals, which are really just probability distributions of where the electrons can be, but they're not that well defined. So you might have an orbital, and I'm just showing you in 2 dimensions, it would actually be in 3 dimensions, where maybe there's a high probability that the electrons, where I'm drawing it in kind of this more shaded in green, but there's some probability that the electrons are in this area right over here, and some probability that the electrons are in this area over here, and let's say even a lower probability that the electrons are over like this over here. And so you might say, well, okay, at a moment the electron's there, the outermost electron, let's say, is there. You might say, well, that's the radius. But in the next moment, there's some probability, it might be more likely that it ends up here, but there's some probability that it's going to be over there. And then the radius could be there. And so electrons, these orbitals, these diffuse probability distributions, they don't have a hard edge. So how can you say what the size of an atom actually is? And there's several techniques for thinking about this. One technique for thinking about this is saying, okay, if you have two of the same atom that are, or of the 2 atoms of the same element that are not connected to each other, that are not bonded to each other, that are not part of the same molecule, and you were able to determine somehow the closest that you could get to them to each other, so without them bonding, so you were kind of see what's the closest that they can kind of get to each other. So let's say that's one of them, and then this is the other one right over here. And if you could figure out that distance, that minimum distance, without some type of, really, I guess, a strong influence happening here, but just the minimum distance that is that you might see between these 2, and then you could take half of that. So that's one notion, and that's actually called the van der Waals radius. Another way is, well, what about if you have two atoms of the same element that are bonded to each other? They're bonded to each other through a covalent bond. So a covalent bond, we've seen this in the past. The most famous of covalent bonds is a covalent bond. You essentially have two atoms. So that's the nucleus of one, that's the nucleus of the other, and they're sharing electrons. So their electron clouds actually overlap with each other. So in a covalent bond, the electrons in that bond can spend some of their time on this atom and some of their time on this atom right over here. And so when you have a covalent bond like this, you can then find the distance between the two nuclei and take half of that and call that the atomic radius. So these are all different ways of thinking about it. Now, with that out of the way, let's think about what the trends for atomic size or atomic radii would be in the periodic table. So the first thing to think about is, what do you think will be the trend for atomic radii as we move through a period? So let's say we're in the fourth period and we were to go from potassium to krypton. What do you think is going to be the trend here? And if you want to think about the extremes, well, how do you think potassium is going to compare to krypton in terms of atomic radius? I encourage you to pause this video and think about that on your own. Well, when you're in the fourth period, the outermost electrons are going to be in your fourth shell. Here you're filling out 4s1, 4s2, then you start backfilling into the 3d subshell, and then you start filling again in 4p1, 4, and so forth and so on. You start filling out the p subshell. So as you go from potassium to krypton, you're filling out that outermost fourth shell. Now what's going on there? Well, when you're at potassium, you have 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You have 19 protons and you have 19 electrons. Well, I'll just do it as, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But you only have one electron in that outermost, in that fourth shell. And so let's just say that's that electron at a moment, just for visual. It doesn't necessarily have to be there, but just to visualize that. So that one electron right over there, you have 19, and you have 19 protons. So there's going to, you have some, I guess you could say, Coulomb force that is attracting it, that is keeping it there. But if you go to krypton, all of a sudden you have much more positive charge in the nucleus. So you have 1, 2, 3, 4, 5, 6, 7, 8. I don't have to do them all. You have 36. You have a positive charge of 36. Let me write that. You have plus 36. Here you had plus 19, and you have 36 electrons. You have 36 electrons, and I've lost track of them. But in your outermost shell, in your fourth, you're going to have the 2s, and then you're going to have the 6p. So you have 8 in your outermost shell. So that'd be 1, 2, 3, 4, 5, 6, 7, 8. So one way to think about it, you have more positive charge in the center, and you have more negative charge on that outer shell. So that's going to bring that outer shell inward. It's going to have more, I guess you could imagine one way, more Coulomb attraction right over there. And because of that, that outermost shell is going to be drawn in. Krypton is going to be smaller, is going to have a smaller atomic radius than potassium. And so the trend as you go to the right is that you are getting, and the general trend I would say, is that you are getting smaller as you go to the right in a period. And that's the reason why the smallest atom of all the element with the smallest atom is not hydrogen, it's helium. Helium is actually smaller than hydrogen depending on what technique you use to measure it. And that's because if we take the simplest case, hydrogen, you have one proton in the nucleus, and then you have one electron in that 1s shell. And in helium, you have two protons in the nucleus, and I'm not drawing the neutrons, and obviously there's different isotopes, different numbers of neutrons, but you have 2 electrons now in your outermost shell, and so you have more, I guess you could say, you could have more Coulomb attraction here. This is plus 2, and then these two combined are negative 2. They're going to be they are going to be drawn inward. So that's the trend as we go to the right. As we move from the left to the right of the periodic table, we're getting smaller. Now, what do you think is going to happen as we go down the periodic table? As we go down the periodic table in a given group? Well, as we go down a group, each new element down the group, we're in a new period, we're adding a new shell. So you're adding more and more and more shells. Here you have just the first shell, now the second shell, and each shell is getting further and further and further away. So as you go down in the periodic table, you are getting larger. You're having a larger atomic radius depending on how you are measuring it. So what's the general trend? Well, if you're going larger as you go down, that means you're getting smaller as you go up. You get smaller as you go up. So what's going to be the smallest ones? Well, we've already said helium is the smallest. And what are going to be some of the largest? What are going to be some of the largest atoms? What's going to be the atoms down here in the bottom left? So these are going to be large, these are going to be small. So large over here, small over here, and the general trend is you go from the bottom left to the top right, you are getting smaller.